Now I think you should see my screen. There's still people in the waiting room in the same time, so I will be juggling, but that's fine. So yeah, today I'm going quickly to introduce what the concept is for this series of events, and after that, José Martinez will present machine learning in space operations with a focus on anomaly detection, and we'll have time for discussions and as well as questions during the presentation. We would like this to be a bit interactive, so don't hesitate. So the concept behind PyM AI Darmstadt, the space edition, is that we would like to marry machine learning, artificial intelligence, and space. More specifically, to have talks about how we can leverage from these new techniques in order to make better space system design, manufacturing, testing, and also to improve operation. So for the target audience, I'm really curious to see where you're joining from. So if you can type in the chat from which country you're joining, that would be great to give us an overview. Okay, yeah, the chat. Denmark, Germany, Luxembourg, Italy, Portugal, nice. Netherlands, Italy, Singapore, nice. Pretty late there, right? Nice. Great to see you all, guys. Also, we'd like, the idea is whether you are already an AI practitioner, but you don't really know about how it applies in the space industry, then you can get away from such events, learning a bit more about how the space field works. What are the specificities? On the opposite side, if you are already a space professional, then you will be able to learn about AI possibilities, the challenges and the limits as well. And well, if you're new to both fields, then well, it's great. You will live with a lot of food for thought. So yeah, that's basically the idea. Maybe if you want to type in the chat sort of what are you doing at the moment? So if you are students, if you are more like space students, AI students, or professional, if you want to type in, like if you're an ML engineer, or that would be great as well to have an overview of the audience. Okay, we have spacecraft operations engineer, computer vision, data scientists, great. What do we have some more? Ground station engineer. So not too many students, or are you shy? People trying to transition from a postdoc into a new career, that's great as well. I hope this such event can give ideas to people. So yeah, let's continue. So today's topic will be machine learning specifically for spacecraft operations, but we aim at covering different topics in the future, ranging from robotics and autonomous systems, also NLP, natural language processing, space environments, design, manufacturing, also some more general topics where we learn about career in AI or space and data-driven engineering in general. Oops. Okay, if you want to stay tuned for the following events before we start and we leave afterwards, please make sure you follow the LinkedIn page Rocket AI, where it's the channel through which we will share every event, so you will be notified that way. Also, these events are great for networking, so if you want to reach out to people in the chat, feel free to do so. You can also reach out to the speakers. I'm sure they will be happy to speak about their work, give hints, or even start projects with you. So that's great. And an important thing, if you would like to learn new things and to take specifically AI courses, these events are done under the umbrella of deeplearning.ai community. So we will get some course discounts for people that take the post-event survey. So after the event, if you get an email to do a post-event survey, make sure you complete it so you can potentially get a course discount if you're interested, of course. So I think I did not forget something. So I'll stop sharing my screen. Oops. All right. Okay, great. So now let's talk more action. I would like to welcome José, who I'm super happy to have you here as the first speaker for this event. José is also a colleague of mine at Solenix, and most importantly, he's really a rock star ML engineer in spacecraft operation. He really had a big impact at the European Space Operations Center in order to improve operation. But I will let him to describe a bit of his work. And please make sure that if you have questions, put them in the chat and we'll take them along the way. So, José, the floor is yours.
Yeah, thank you, Patrick, for the introduction. Thank you for having me. So I'm trying to share something and you let me know you can see that, even if I put presentation mode.
Yes.
Do you see the right screen or you see the wrong screen?
No, we see the right screen. It's all good.
Good. So I'll be talking today to you about machine learning in space operations. And yeah, it's a first, if you might wonder, who is this guy? I have like a one slide about myself. So José Martinez is my name. I'm Spanish, computer science by education. And I've been working in DI before it was cool. So when I started working on it, it was called data mining instead of machine learning. So you can imagine. My background is I'm in Solenix, and I've done many projects with ESA. And this is where this angle in space experience comes from. What I prepared for you is because I was checking with Patrick what kind of audience we could expect. Well, you know, it's a bit what Patrick said in introduction. A bit of people who are more in space and want to know more about machine learning, and some people in machine learning want to know more in space, or a mixture of that. So, you know, it's difficult to prepare something that fits to everybody. So the compromise is the following that I did. We have a very short introduction to machine learning, in case you're not familiar with it. And then we dive a bit more on interesting application of machine learning in space operations. We go with introduction. My favorite definition is the one. So we have, as machine learning, the science and even the art of programming computers so that they can learn from data. And how is this different from programming? Well, when you have a program, you have some data, and the program does something with this data and produces some results. When you use machine learning, you have data, a model does something with this data and produces some results. So from the outside, looks like it's the same. The difference is how the program or how the model is built. For the program, you give requirement to a development team, and as it goes, no, like a pizza and coffee and so, and they release a program. In machine learning is different. So you give data, you give examples of the results that you want from this data, and the process of machine learning learns a model that can do this task of transforming data and results. This sounds too good to be true, but the news is that we are not going to replace programmers, software developer anytime soon, because this only work for some tasks. And I give you some example that maybe you are not aware, but you use in your daily life that use this paradigm of having a model that has been automatically learned from data. So some of these tasks is spam filters. Now we get much less spam as we used to many years ago. If you use Amazon or Netflix or so, recommendation engine is another application. Another application could be predicting the real estate sales price. By far, the most popular application is predicting in which advertisement you will click. Image processing, I think it's not news anymore that it has achieved better than human performance. If you have a mobile phone, for sure you use Google Assistant or Siri or even Alexa. And being myself Spanish, living in Germany, I use this translation service all the time, so it's very handy. Yeah, I mean, there are many more tasks for sure, but I just put some of them which were more popular. Some consideration if you're thinking if machine learning is a solution for your problem. And I put 3 of them. So first, there must be a pattern between the input and the output. So you cannot use machine learning to predict a lottery number, for instance, because there is no pattern. And the amount of data should be enough to discover this pattern. So some people ask me, what is enough? It's hard to tell in a way to satisfy everybody, because enough depends on how difficult the problem is and the relationship between the input and the output. So it's enough depending on the problem, let's say. And the other thing is that you want to use machine learning only when you don't have another solution. If you have a way to do it analytically or use a mathematical expression to solve it, then use that instead, because you could get good solutions, possibly which are proven to be correct, while machine learning, it would be only an approximation. I mean, there is an exception to this one, is that if the mathematical expression takes very, very long to compute and you're happy with a fast approximation, this you can go for it as well. There are many ways on how to structure machine learning projects. We happen to like this one. And at the end is, we understand the problem, we identify how we will measure if our machine learning solution is doing right or not. We compare with the baseline. Baseline could be that the current solution or something which is very easy to do. You need to prepare the data so that is friendly for machine learning, let's say. Then you train the models and analyze the error of the models. And you go some cycle of this, and when you're happy, you put this model in production. I put some color in this picture to signal more or less the relative effort. So a lot of effort goes, of course, to put the model in production. and a lot goes in preparing the data. Problem understanding it, I mean, it depends if you join or if somebody from the problem owner can participate in the project. There is a way to improve this aspect. And error analysis, well, yes, you need to understand why things are wrong so that you can get better. Some people are surprised that I put in green, like training models or create models is like a slow effort. I mean, it might take a lot of computing time, but I'm putting here only human time. And yeah, it takes so few human time because there are thousands and millions of man hours or human hours, let's say, put together in open source libraries that we can use. So this is a big thank you to the open source community. Yeah, this was for the very short introduction. And talking about machine learning in space operations, maybe it's good to describe the data. And most of the projects have been involved using at telemetry data. So telemetry data looks something like this, a time series, similar to stock market, let's say. And they measure that sensors at the end. Could be like temperatures or voltages, currents, these kind of things. There is more stuff for data, so you can check, for instance, which are the commands, so what the spacecraft was asked to do, or which are the events, or what the ground station is measuring, or what the temperature of the ground station is. I mean, there are many things, but in this presentation, we're talking mostly about telemetry. So some examples about prediction, and I start with prediction because it's if you're familiar with machine learning, maybe this is the easiest one to understand. And one example is we helped ESA to organize a machine learning competition to predict the thermal power consumption for Mars Express. So why is this useful and it's also difficult? Well, it's useful because of the formula that you have here downstairs, is that we know how much power it will be produced. We know how much is consumed by the instruments and the payload and so, but what is unknown is how much power will be consumed by the thermal subsystem. And why is it unknown? It's unknown because it's a bit critical. So you need to keep the temperature at certain location of spacecraft within boundaries. And it's a bit delicate, so it's not commanded from ground. So it's a bit like the air conditioning in the car, if you like, that you say, I want this temperature, and it automatically switches on, switches off. So this climate. And it's the same mechanism. And it depends what the satellite is doing, and the orientation and distance to the sun, and which payloads are active and so. And there is a lot of coupling. So it's a difficult problem, but if we will reduce the uncertainty on how much power will be consumed by the thermal subsystem, we can use more instruments simultaneously in a way that is still safe. And we organize a competition, and there are some teams from all over the world who participated and has been proven successfully. And ESA now is finishing actually a project that is implementing the solution from the winners to be used in operation by Mars Express.
That's really interesting. Huh? This application. So actually, what if I try to summarize, is by improving the accuracy of prediction on the thermal power. This allows to reduce the margin that we put on the power allocation for the thermal control subsystem, and therefore this allocation we can devote it to do more science. Or okay, great. Yeah, that's really nice.
Yes, indeed. Another competition we help organize is the to avoid, let's say, or to predict which is the risk of space debris colliding with ESA-operated satellites. And I mean, it was, I mean, now it's over, but it was very successful. But the problem was quite difficult, I have to admit, because the data is, in this case, was very unbalanced. So we have a lot of cases where the risk is extremely low, and very few cases when the risk is high, and which is great for operation, let's say. But machine learning has difficulties to understand this unbalance. I mean, and there were some of the issues. I've seen that Luis is one of the participants here. He was one of the top ranked participants in this competition. If you want to know more, I think Luis Simões can tell you more about that.
Oh, great. Nice to see you, Luis, then.
So another thing that we predicted is the entry and exit in the radiation belt. So we have, or there are some satellites which cross the radiation belt, and what happens in this belt is that there are some electrical particles which are charged and that get trapped because of the magnetic field and so. And if the instruments of a satellite encounter this charged particle, they could be damaged. But I mean, it's not a problem because this is known before we launch the spacecraft. And there are mechanisms to protect the payload. So every time you are in the vicinity of the radiation belts, they are covered, and you know that nothing will damage them. So the issue is that it's the same thing again of the uncertainty, because they're not fixed in space, so they are sort of briefing. And if we will know where the radiation belts are at each time, we can keep the instruments working for longer. So we can do more science and also not being in a risky situation. So by predicting the entry and exit, then we reduce this uncertainty and do more science.
And did that project work well as well?
Yes, the results are good, and we will have, or let's say, ESA will have a final presentation on next month. On this one is being implemented by the winners of the Mars Express competition. I mean, we did, or let's say, we support like an initial prototype, and they are doing the operational implementation.
Okay, that's really nice. And so you mentioned these competitions. Is that sort of competition opens to everybody, or can you talk a bit about this?
Sure. Yes, maybe I can put it on the chat. No, I cannot. No, I cannot put it on the chat while I'm presenting.
I can find the link.
I can put it later. It's a website, Kelvin's ESA Int, that ESA publishes the competitions for machine learning. And yeah, you can have a look and see what is open. It's quite interesting, I have to say. And I've helped preparing the data for some of them. And sometimes it's, let's say, most people are not aware on how tricky it is to prepare data for machine learning competition. It's a whole of a science, let's say.
I can imagine.
But I mean, this goes for a different topic, let's say.
Yeah, but and I see that there is actually right now as well a new competition running, which is dealing about estimating the pose of a satellite. Mm-hmm. So if some of you wants to compete and challenge yourself, yeah, maybe that's a way to do it.
Absolutely. So, and it's a lot of fun. If you never participate in a competition, it's a lot of fun. So I go for the next. is this is a deep space antenna. This one is in Malawi, so in Argentina, and these are big antennas. I don't know if you see the mouse, but
Yes.
here down to the left, you see a person. And yes, this is a bit for context for you to figure out how big this thing really is. And the issue is that this we need so big antennas so that we can communicate with deep space satellites, which are so far away. That's why you need a so big dish. And that's so far away that the pointing needs to be very, very precise. And if you deviate a bit, then you lose some data, let's say. What happened at this location is that it's very close to the Andes. So the Andes are the mountains that you see in the background. And sometimes you have a high wind blowing. And when there is this high wind, this can move a bit antenna and you can lose the fine point that you need, especially when the wind is very, very high. So something that we did was check if we could predict what will be this deviation so that we can be, that it can be compensated. And I mean, it's not yet fully implemented. We arrived to the level to say, yes, we can predict it, but it now needs to be, let's say, put in a control loop, but the prediction is there. And it works. We were surprised because we were not hoping to get the good results that we get, and they're so much better than we expected. So we're very happy about that.
Indeed. I assume it must not be that easy that from demonstration, because what you've done is like a demonstration or a feasibility study. Then going, you say it's not yet implemented in a control loop. I mean, do you know what make it hard to actually deploy it into the system? I assume qualifications or.
Well, there are some things is you will need to. Well, what we found is that the predictions to be useful was with a lead time, or let's say, or a latency of 250 milliseconds. So, of course, when we have the data, we make the predictions. But when you have this in reality, you need to make this prediction at this speed, let's say. And I mean, this should not be a problem, but you need to make sure that the data also arrives at this speed. And also, when you want to do the corrections, is not, by knowing the prediction, is not that you can correct everything. So maybe you get only like a 25% of improvement just because of how the mechanics work. I have to say I'm not an expert on the antenna side, but I've seen that there were some people here from ground station, so maybe they know better.
Sure, maybe that's a way to to promote this system.
So I go to the next one. Something that I was doing that was a bit different on the area of natural language processing is to predict which articles will receive a high number of views. This was done in collaboration with the ESA Communication Office. And yes, they wanted to know what made people tick, let's say. So can we know if an article will be popular even before publishing it? And what we found was a bit not too surprising, let's say. And is that when we have, was at the Rosetta time, no? Topics about Rosetta, comet, surface, lander, black holes, and these kind of things, people love that. When the articles were talking about ESA, technology, companies, it was not that popular, let's say. But I mean, it's something that you see in the data. Okay, this is let's say sort of a more classical machine learning problems, classical in the sense that they are supervised. So supervised in the sense that you have your data, you know what the expected result is, and the machine learning techniques, they learn by knowing how wrong they were. So it's classical in this sense. A bit more tricky is the anomaly detection, and I spent some time to tell you why it's so tricky, let's say, and that I put in the challenges part. So what's an anomaly? And you know, an anomaly, some people say, well, it's a deviation from specification or something, a get out of control. But after working so many years with space control engineers, my definition of what an anomaly is the following. We didn't want this to happen, whatever this is. And just to be complete, I put also this one. We wanted this to happen, but it didn't. But it's really the first. So we didn't want this to happen is what they really mean by anomaly. Yeah, you know, is that machine learning does not know what is that you wanted or what people wanted. So instead of doing anomaly detection, we make a trick. And instead of solving the problem of anomaly detection, we transform and make a problem easier. We solve the problem of novelty detection. So we tell you when something is unusual, when something is novel. And yeah, what we found is that more often than not, when you have an unusual behavior, it is usually the signature of an anomaly in the way to happen. So we make a bit of an easier problem, but it's close enough still to be useful. The other challenge is that you know that in spacecraft, something will eventually break. And you know, even before you launch it, because usually they are designed maybe for 3 years. They are designed for 5 years of useful life. But since they work so well, you end up using it for 15 years, 20 years. So you're using it like twice as long as you should be using it. So something eventually will break, but you don't know what or how or when. So yes, we are faced with first-time anomalies. And the first-time anomalies are the one that impact people the most. And so the first-time anomalies, I mean, is anomalies that nobody thought that this could happen. Or if they thought this could happen, they didn't know how they will detect that. And this is very different from normal machine learning, because normal machine learning is that you know what you want to recognize or the pattern you want to detect from the data, and you have enough data and you recognize this from the data. But this is not our case. We are looking to detect the first time ever that anomaly happened. Possibly this will not be seen again, because once the flight control team understand why this anomaly happened, they will try to operate the satellite in a different way so that it doesn't happen again. So we are always facing the issue of detecting first-time anomalies that are not recurrent. The other challenge is false alarms. So whatever system you have for detecting anomalies, there will be some false alarm rate. And people totally hate false alarm because it takes time to investigate. And I said, at the end, it's for nothing. And if you have too many false alarms, at the end, people stop having a look to the results. And to put you an example on how bad this can be is, imagine we have a system that detect the alarms correctly 99% of the times. Well, for us, this would be pretty useless, let's say. because it will mean that 1% of the time it will be wrong. So just to make you the math, there are about 40,000 telemetry parameters. And if we check for anomalies like once a day, we get 400 false alarms. So it's it has to be better, let's say, than 99%. The other challenge is sometimes machine learning finds something is unusual, but it's not obvious to people why. And what we found is that it needs to be obvious, otherwise there is some lack of confidence in the results. Yeah, this is about the challenges, so we want it to be obvious. And I show you now a bit for those of you who are not familiar of the out-of-limit approach. This is the classical approach on how this is done. I mean, it's quite simple to understand. So you have the signal there in the middle, and you can define some threshold. You can say, well, send me an alarm, or the mission control system say, set an alarm when something exceeds the soft limits or the hard limits. And you can make this a bit more intelligent about depending on the behavior or the status of the spacecraft, use different limits. You can also do that. The issue is that sometimes you have anomalous behavior, which are in limits, and then there is no way to detect them. So I can tell you how we're doing it, and how we do it is not necessarily the best approach, but it's something that so far works.
Before we move on, can you tell us a bit more about what the difference between soft and hard limits are, for those who are not super familiar with this?
Okay. Well, soft limit is nothing's gonna break, but I want to be notified that this value is approaching the breaking point. Let's say, I mean, it's not that it will break also if it goes to a hard limit in a deterministic way, but let's say it shouldn't go to hard limit, and this hard limit in many times set by the manufacturer of the spacecraft. And soft limits is that you don't want to get close to the hard limits. That's why you put them to have a bit more of time to notice that this will happen.
Okay, yes, sure. Yeah, Javier is saying it's a bit like a warning, an early warning, and then it's the alarm where we say, no, you really should pay attention to that, investigate it right now if it hits the hard limits. So, okay.
Yes, and I mean, this is the classical approach. There are also some limitations to this approach. For instance, only some parameter has out of limit. So the majority of them, they don't have out of limits. Also, as the mission degrades, because with time, you have less power in the solar arrays, less power in the batteries, or you have some other degradation. You need to keep updating for those. And yeah, and also is sometimes people use it in the wrong way. So let me explain what I mean by use out of limit in the wrong way. When you go, for instance, you're communicating with the spacecraft, with the ground station with the spacecraft, and you lose the signal, and this is foreseen because the spacecraft moves, so it's known, and it says alarm. I lost contact with the spacecraft, and some people use this as a confirmation that the past is finished as they should, but it's not really an anomaly. I mean, it's part of the design of the mission. So this is a bit what I mean.
Okay.
Yeah, we use this approach that we have time series, and we compute some simple statistics around that, like a mean, standard deviation, maximum and minimum. And for the sake of simplicity, I put like a mean standard deviation there. And this is every dot correspond to one of these periods, and this period could be like a 1 day or so. And so 1 point, it would be like one period here. So usually what happens is that some sensor, depending on the working mode or depending on the status, they have different working modes. And on the left, it could be like when it's in this working mode, on the right, when it's in the different working mode. So something we can do is we can represent the data of today. And we say, okay, the data of today is very different from what we are used to. So let's call somebody. And we know that this distance is wrong. The issue with this approach is that if it will be there and I count the pixels to make sure there was the same distance, here we will say it's all fine. And the intuition behind is that here when it's on this state, everything is very similar. And here on the right is very diverse or very dispersed. So if we use an approach that compute distances, whatever threshold we set is going to be wrong. So the intuition here is that we use the density-based layer detection approach that take into account the density to automatically decide when something is anomalous or not. And in fact, the approach that we use is called Localized Probabilities. And this is originally researched by, I'm reading here the credits from a German university. And in the paper, they use it to identify which are the outstanding soccer players. They want to find which are the best soccer players, which are still cheap to buy them, buy teams. No? But I mean, we repurpose them for space. And what you see here are probabilities of something being unusual. What we like about this technique is that it makes no assumptions on how nominal behavior should be. There are many approaches that they require that the data follows a Gaussian distribution or a normal distribution. We know our data is not a Gaussian. I mean, some parameters could be, but we cannot make the generic rule, and many of them don't follow a Gaussian distribution. It also takes into account that parameters can have different nominal behavior. You see here on the left, it's nominal, here is nominal, here could be also nominal. And with the density, we don't need to put any threshold. So we are relieved that we don't need to specify any threshold. And the other thing that is useful for this approach is that we get probabilities of something being unusual. So this allows us to prioritize and compare what flight control engineers, they can look. So we can say, look at this temperature and then at this voltage. Well, you cannot compare them, but you can compare how unusual they are. Okay. And to compute the density, basically we compute which are, how close they are, the points around on the vicinity of each point. And this leads me to the magic sauce to reduce the false alarms and increase the obviousness. So something that we found is that to compute the density, we need to choose how many points we take in the vicinity. This is an hyperparameter scale, let's say. And it's a bit arbitrary. We can take 5, 10, 20, 30. There is no right or there is no wrong setting, let's say. So what we do is we check 5, 10, 20, and 30. And we require that it should be anomalous regardless this hyperparameter. And what this brings us is that it makes more obvious because we make the assumption that if it is obvious, it shouldn't matter which hyperparameter we tune or we choose. There are other people, I mean, I was talking to Alexandra from DLR, and they have a different approach. What they do is they have overlapping windows. So they check that there should be anomalous in a time window, and then they shift, and it has to be anomalous in all three. And this is also a way to increase the obviousness of the results that people really appreciate and reduce the number of false alarms. I mean, we can visualize data like that. So we can show this was unusual, and this is how we represent it. I have a couple of examples here. So this is coming from XMM. So it's a astronomy mission at ESA that is looking at the stars in a, let's say in a elliptical orbit. And what you see here is a temperature connected to a problem that I tell you before with Mars stress, no? That is keeping the temperature. So every time that it arrives to 30 degrees, it opens the circuit. So then the temperature cool down. When it goes around 24, it closes the circuit again and start heating. And you have this cycle going and going. And this is a very simple behavior. And I like this one because it's never, you couldn't have never catch this anomaly happening going here down with out of limits, because the anomaly is that it was more in limits than before. So we have the out of limits here. And this was a bit too late. We checked that with this approach of anomaly detection, novelty detection, and we found this, let's say, wrong behavior 2 months in advance. On the other hand, I mean, you cannot count on this. This happened to be like 2 months in advance, but when you have the new behavior, you have no clue if it will lead to an anomaly or when the anomaly will be. But I mean, you know that you should be paying attention to that. And this is a very simple example. And I can think that if you look at it, you have plenty of ideas on how you could check it in an easy way. But the challenge is have a system that automatically can detect unusual behavior in any kind of behavior, let's say.
Indeed. Jose, we have a on this. So we have a question from Yara, who is asking related to the challenge on of obviousness in the chat, asking if the operator is not sure about the root cause, how can we be sure that the anomaly detection model generalize well, especially considering that it's just trained on the available data and the feature space?
Okay. Well, we don't know. So basically, the input that we are taking from the user is example of nominal behavior. So we ask them, tell us what you feel it was nominal, and we take this as a ground truth. And if it happens that there was something false and there was a wrong detection, we ask people to say, well, now this also belongs to the nominal behavior, so that this is considered. And yeah, that is not, let's say, signal again as an anomaly. So this contributes to the obviousness, but it's not so much that we have training because there is nothing to train. So we don't have a model. It's more like it uses the data. So we have all the data and we pre-compute the statistics and we do these comparisons once a day. So this is how it works. Okay.
Yeah, so we have a pool of nominal behavior, and when we detect that something is suspicious, there are the experts, the flight control teams, spacecraft operator, they run this investigation and decide whether or not it can go into the list of acceptable behavior, because maybe we haven't defined out of limits, or it's actually acceptable or not. And then it goes back to what you said in the beginning. If it was actually anomalous, they try to resolve it and operate the spacecraft in a different mode so that it doesn't happen again.
Yes, and I see another question is, how many dimensions of features can you implement? Well, the answer is that any dimension work. So we use these 4, like a minimum, maximum, average, and standard deviation normalized. but you can use as many as you like. But I will recommend against that because of the curse of dimensionality. So the curse of dimensionality means that what means is an effect that has been observed that as you increase the number of dimensions, the data that you need increases exponentially, because otherwise every point needs to be, oh, let's say when you have many dimensions, every points appear to be at the same distance that any other point. And then since this technique is based on computing distances, everything fall apart. I understand it can be a hard concept to get. Maybe you can visualize like this. When you have a pen, so let's say one dimension, and if you have one point here, and you have another one there, there is like one only way. If I tell you the distance is 3, it's either here or it's there, so it cannot be anywhere else. If you have a plane, like this, it can be like in many different places. But if you have 3 dimensions, 4 dimensions, and so, there are many opportunities that you find points at exactly the same distance. And the more features, the more dimension you use, the more and more meaningless the distance is.
Okay. Yeah, very interesting analogy. Also, one question that popped into my mind when you presented is, you said you compute statistics over some windows. Did you tune these windows, or how do you make this choice?
Okay. Yes. At the beginning, I was thinking, let's take orbit because it makes sense. No, it feels right to use orbit because then you exploit the periodicity of the behavior. No? And this worked great because we applied to XMM, has an orbit of 2 days. Then we applied to SMOS, and it fell apart. It didn't work at all. And so why? We're using orbit, and now we're using orbit. And SMOS is a Earth observation mission. And it is about 90, 100 minutes, the periodicity. And this was a bit too fast in the sense that statistics were not stable enough. So and we changed it to 1 day, regardless of the orbit, let's say. What we found is that there is another periodicity, which is a periodicity driven by people. It's how people operate the satellite. And this is, we can also exploit that. And it's more like in daily basis. But the message is select a periodicity for the features that maximize the stability. So if whatever you bring more stable, then this makes easier to find unusual behavior later.
Okay, thanks.
Yeah, I go to another example, and I brought this one because of the simplicity, and this one is because it's one of my favorite. What you see here is the ATV going to the International Space Station. And I mean, it does many things like bringing oxygen to astronauts, quite important, and supplies. And it also pushes up the ISS, not to prevent it from falling down. And talking about oxygen I didn't know at that time, but we human beings, we cannot breathe pure oxygen, otherwise we will die. So for this reason, in the ATV, there is a fan that mixes the oxygen for the astronauts. And what happened is that this fan broke, and so many 100 kilos of oxygen couldn't be used. And they asked me, could you have detected that? So, well, let's see. So they gave me the data. We ran this novelty detection algorithm, and yes, of course, we could have detected the fan before it broke. But for me, the most interesting aspect was that 1 week before the fan broke, we detected unusual concentrations of particles in the smoke detectors. And this was something that nobody thought about, and we found automatically that by monitoring the smoke detectors, you can tell that the fan was not working properly. And this is sort of post-predictable in the sense that now that I tell you, it seems obvious, but it was not at that time, let's say. And it's good that we can find this kind of connections automatically. Yeah, this is for novelty detection. Before I change topic, I can say something as for novelty detection. Is this the very best way to do novelty detection? Well, possibly not. I mean, DLR has the way, KNES has the way, UMSAT is a lot inspired by this approach. But in reality, it's very difficult to know which way or which approach is best, because there are very few anomalies in reality, which is great. I mean, for space operations, it's great that you don't have anomalies, but it's difficult to benchmark with real data. So for this reason, we influence a bit ESA on this aspect, and ESA is starting soon a project to curate a data set with having anomalies from several missions. We did a small prototype doing from one mission, but now this would be enlarged and extended with many missions. And the idea is that this data set will be available for people to try different approaches.
Very nice.
So diagnostic, this is also not typical at all of machine learning. It's more data analysis, but I think it fits here. And yeah, the idea is that we want to support operators in finding out why the anomaly happened. And the assumption is, well, if there is an anomaly and we have access to the data to all the 30,000 telemetry parameters and events and telecommand and so, maybe something else holds the key to understand the problem. And we made some data analysis to check if this is true and eventually find the reason for that. And the assumption that we make is quite acceptable, is since there are so many parameters and we want to find those which are involved, we assume that if a parameter behaves the same during nominal periods and during anomaly periods, this parameter has nothing to do because it doesn't change. It's regardless anomaly or nominal. But if the behavior is very different in nominal periods and anomaly periods, maybe there is a connection, okay? And well, how we do it is a bit like this, is we put T for target, N for nominal, and we check some statistical features. So for instance, we compute here, is the minimum different from nominal to target? No, it's the same. So the minimum doesn't tell us anything. Is the maximum very different? Yes, it's very different. Here is the other way around. In this other parameter is the maximum doesn't matter and the minimum does. So we go like parameter by parameter and we check when there are statistical features that have a pattern, and the pattern is that they're very different during target and nominal periods. So the result at the end is that we analyze 40,000 parameters and we say, look at these 7. So to the flight control engineer, it looks like that we found which 7 parameters are involved in the anomaly. In reality, what we did is we discarded the one that we know for sure are not involved. So this is a bit of different perspective, but it's the same coins seen from 2 different sides, let's say. And yeah, this is a an example coming from Venus Express. And at that time, it was what you see in the red plot is the attitude error, so orientation error. And at the time was not that clear why this happened. So we ran this analysis at diagnostics, and we found that every time that the scanner was initialized, it was introducing a torque. And once you see that, of course, it's a scanner. So the scanner introduces a torque, and this is what changed the orientation. So it's obvious after the fact, but many people in operation, there is kind of, I wouldn't say religions, but there is a mindset that they don't think, or at least at that time, as a payload, as the first reason for something to happen in the platform. But yes, it's once you see that, it's obvious to them. The other thing is that even if the initial intended use of this diagnostic tool was to help people identifying reasons for anomaly, we noticed that some other teams started using it in a different way, started use it for characterization, because at the end is comparing what is the behavior of nominal periods with target periods. No? And then you can say, okay, let me show which parameters are affected by solar flare. So solar flare, even if it's not really an anomaly, it's something you know before you launch the spacecraft that will happen. You say, okay, this anomaly, I take solar flare as a target period, not solar flare, nominal. And I find, for instance, that the number of bits error corrected and detected is showing this plot, and some other parameters are affected. You can do the same thing for South Atlantic anomaly, or when there is eclipses, and you can find a way to characterize like different behavior. And also in this aspect of diagnostics, I don't go too much in the details, but we did something like this. It's finding which are dependencies among parameters that can predict if I change something, what else will change? And you have this sort of change effect that can be anticipated. But I mean, it's a bit tricky, and I think it takes long to explain. So I think this is a bit of a summary of what we discussed. And this is maybe sort of an icebreaker. Now I think it comes the interesting part of the discussion where you can contribute. I don't know, Patrick, I'll leave it to you to organize. Last thing for me is let's stay in touch. If you want to reach or connect, here it is. So Patrick, ball is yours.
Thank you very much, Jose. It was a very interesting presentation. I really love it because it gives a nice overview of a broad spectrum of application, from news, from predicting views of news in the communication department, and to prediction of power consumption anomaly. So it's a really great presentation. So now, if the audience has some questions, I invite them to put them in the chat, or even if you want to directly ask a question and want to unmute yourself. Okay, Leo is asking, for mission where you are checking 30K plus parameters, how many false positive do you see on average per day?
Yeah, it's a good question. I will say it depends on what is it that it's doing and how people are using it. So it takes some time to configure it, in the sense that when you initially use it, you have many false alarms, because I mean, it's not, you don't have the data still there, no? Or maybe you say, take anything from January to March as nominal, but this is possibly too small data. Or then as when you go in this process of say, well, there are many false alarms, then we go again and we say, okay, this in reality was nominal. Then next time you run it, you have less. And the more you use it, let's say you have less and less and less. The other thing that, I don't have a number, let's say. The other thing that can increase heavily the number of anomalies is that when you do something very different. For instance, if you go into Jupiter, it's a lot different going to Jupiter than orbiting around Jupiter. So when you have these changes in phases, it makes everything very different as well, even if everything is nominal. Because we are not doing anomaly detection, we are doing novelty detection. So it's unusual compared to a reference period. Yeah, I mean, it's hard to tell.
Yeah.
But what we found is, for instance, most use it quite extensively, and maybe they have like 3 anomalies to check sometimes, maybe none, depends on the day, you know? And yeah, we found sort of magic number, whatever is below 10, people like it.
Nice. Thanks for this answer. So I assume you cannot directly use that on the first day of the mission. You have to wait a couple of weeks or months until you have a baseline with a couple of nominal behaviors.
Yeah, indeed. I mean, at the end, it's based on data, so you need the data.
Sure, sure. Are there any more questions? Yes, Carlos is asking, have you used LOP for analysis, for analyzing telemetry in real time?
No, not really, because what we found is that when we detect anomalies, they take time to develop. So let's say if there is an unusual behavior, as we've seen before, it takes like 1 month for the anomaly to develop, or this case for the ISS, it took like 1 week. So we found that checking it like once a day is good. And for doing real time, maybe it would be a bit computationally expensive, because it takes like 10 minutes to run. And yeah, you can only run something every 10 minutes. So it will not be also real time, but it was mostly because we didn't have the need. But in principle, you can run it as fast as you like.
Okay. So for the moment, we don't have more question. I'll take one. So there is a phase in the preparation of the mission where we do simulations. So I don't know, is there a way that we can anticipate what would be some nominal behavior to pre-fed such algorithm with expected nominal data?
Yes. So what you're saying is that you can use simulators, sometimes not as real or as realistic as we want, or depend on which subsystem. But something you could do is there are sometimes missions which are constellation of missions. So you can use another satellite, which is possibly the same platform, and as an initial data for a new launch satellite. And this for constellation will work.
Oh, great. Yes, indeed. And we are in our era with more and more constellations.
Yeah.
Mark is asking, are most missions using such technique newly launched, or are old legacy missions showing interest to upgrade? Not sure I understand.
Maybe I do. Well, maybe I can show my understanding, and then Mark can tell us if we got it wrong.
Yeah.
I would say that all missions are the more interested in this, because the older missions, they have the high interest, let's say. They have more the risk that something will break, while there is this typical bathtub. So this shape is like this, no? That errors or problems that you usually have the error at the very beginning, and the conditional probability of the mission surviving, provided that it has already survived, are very high. But when it comes to later stages, everything starts breaking, you know? So it's like this. And the older missions, I think that they're more interested because they are aware of this error rate and this distribution of error over time, and they know that they have more risk the longer they go.
Sure. Yeah, that's a very interesting insight, indeed. Matteo is asking, it's great to see questions from the chat. So thank you guys. Matteo is asking, do you see a generalizable way of implementing ML algorithm for anomaly detection that can work for different kind of platform? And if yes, what would be this way forward?
Oh, maybe Matteo, can you elaborate what you mean by different kind of platforms?
If you want to take the mic, you can as well.
Also,
Matteo.
take the mic, we go faster.
Hello, yes. Can you hear me?
Yes.
Sure.
Great. Yeah, the point is to not have exactly the same platform replicated in a constellation, but to scale these kind of approaches for, let's say, different kind of size of the satellite, or even if the core subsystems are the same, but maybe they have different interfaces and stuff. I know it's a bit general, but
No, I see what you mean. So is that what you're saying is it almost the same platform, but not quite the same? At this moment, I see it quite tricky. I mean, you can get sophisticated and say, well, you know, I will learn machine learning models that learns to translate my old platform in the new one. So like taking as a prediction problem, but no, this is maybe too cumbersome, or it's too much of an entertainment for work. No, I don't see now how this can work from the top of my mind. But I mean, at the end, this is a discussion. If somebody has an idea, feel free to jump in.
Sure.
Thank you for the answer. I know it's a bit of a broad and
no, it's tricky. I mean, I understand, because this will give you a way to use anomaly detection from the very beginning. Yeah, but I don't not say that it's not possible, but it requires more thought. Let's say I haven't faced this problem yet, so if somebody did, I think it's good.
Another,
I see, Mark.
Yeah, another question, which is I think very interesting for everybody.
What's favorite machine learning places to hang out online? Hey, well, you know, this event that Patrick is organizing is under the umbrella of deep learning AI, and they have fantastic courses. Yeah, I've done some of them, and I love that. So these are good. They have some newsletter. It's called The Batch from Deep Learning, which is also very good. And sometimes where I go is I go to Paper with Code, this as a website, because you know, there was some reproducibility crisis, let's say, that means that some people claim some stuff in papers and there was not really, or this could not be demonstrated, let's say. And this paper with codes is paper and is code. Ah, yes, it's a paper with code. I can write, yes, papers with code. Is maybe somebody can check, ibet.com, but if you put paper with code, and like this, you have like state of the art that you know it works. I can give you an example. I found a paper from a guy who said that he could predict stock market, and I read the paper, and I said, "Well, this is easy enough. I could do that in 1 hour, and in 1 hour I can know if it is true or not." So I implemented the paper, and I realized there was a mistake in the way they did it. I wrote the authors, and that's well, you make this mistake. That's why it looks like you can do it, but in reality you cannot. No? And yes, like this, you have sort of a state of the art. But I think this is a good question also to be answered by other people. So if you know other good resources, Patrick or somewhere else, put it on the chat.
Oh, yes. Nice call. Feel free to share your favorite places to keep learning and network as well. In the meantime, I don't know how many people we have in the chat who are looking to transition maybe or to work in the space sector, but who don't know it yet. So what would you say make it very particular or unique working in the space sector, different from other projects that you've done in other types of or other industries?
I will say that it is very conservative, but it's for very good reasons, because it really matters if you have something wrong, and you always need human judgment. So you can use machine learning to make recommendations, but I see it difficult for automation, because, for instance, if Netflix recommends you the wrong movie, or if Google shows you an advertisement that maybe you will not click, well, no big deal. But if machine learning does something wrong with the satellite in an autonomous way, this can be very impactful, let's say. So this is the difference is that there are high stakes, let's say.
For sure. We have Ali who is asking if machine learning vision and especially image recognition area is used in space missions.
Sure. There are many applications and that use let's say image recognition and computer vision and a lot of convolutional nets. But what we discussed today was more like AI in space operations. And space operation, if you do the analogy, let's say, instead of a satellite, being a satellite, let's imagine it's a car, then operation is like driving it. I mean, it's not quite the same, there is more to it, but it's more the analogy, you know? And the operations usually doesn't concern itself with analyzing data or from instruments. It's more like making sure that the satellite works, say, in an efficient way, and that the scientists can make use of this platform to do science and leaving the science to them. So there is this split that ESA does. It doesn't have to be this way. There are other institutions that they do everything, that they do operations and the science and dissemination, and even they analyze all the science, but ESA split, let's say, between operations and science. Yeah, I happen to be working on the operations side, so for sure it can be used, but it's not, let's say, my domain of expertise.
Yeah, a couple of insights from my side of what I've seen in the domain so far is some people attempting to use images to improve landing, like entry, descent, and landing for like site selection, or to discriminate between if you approach down the lunar surface and you want to avoid a crater. So I'm not full up to date with this topic. Maybe it's a good excuse to invite somebody who knows that for one next event. And then, of course, for everything which is related to Earth observation, you will find a lot of Earth observation data set online, which you can easily start to play with. And so that's yeah, a big area. It's a bit more tricky to find data related to operation, like telemetry like data. If you want to play with such kind of data, then go ahead and have a look at this Kelvin competition, ISA Kelvin competition. And actually the one running right now is about analyzing images. So calculating the pose, the attitude of the spacecraft by looking at images. Yeah, maybe for space debris as well, this for sure. Great. Is there anything else that somebody wants to ask, or maybe José, something we haven't asked you would like to tell us, or a final word?
Well, thank you for having me. Let's stay connected. You have there my contact if you like. And looking forward to meeting you. And you know, it's very interesting and very exciting to work in machine learning and space. So I think today you're doing great by attending to this event. And Patrick will be running a series of events on this topic. So I hope that you enjoy them as well.
Sure. Thank you very much for opening this series. So thanks, José. It was super great. People, you can have a round of applause with this icons thing. I haven't tried yet, but I will try. And if you want to get notified and don't miss any future events, try to follow the Rocket AI LinkedIn page, or just look at the deeplearning.ai events, and we'll try to publish ahead of time. So thanks everybody for joining, for all your very interesting questions, and thanks José again, and see you soon. Have a great evening.
Happy Tuesday.
Bye-bye.